today on Startup Report is Karen Zaderej, who's the president and CEO and chairman of the board for Axogen. Welcome.
Thank you. Happy to be here.
So we've been following you for the last year or so, based in Tampa. The company is growing and coming along quite nicely. Before we dig into the latest, let's look at a brief overview of Axogen so we can go get on the same page and we'll go from there.
Sure. Well, we're a biotech and medtech company focused in the area of peripheral nerve repair. A lot of people don't know what peripheral nerves are. So to help understand what they do, it's the wires of your body. So it carries signals from your brain to let your muscles move or to give you feedback about the environment, sensation, vibration, temperature, all of those things are signals that are carried on the peripheral nerves. We have 4 commercial products that surgeons use to fix nerves when they're damaged.
That's great. And how old is the company?
Well, we started in Gainesville. We're a spin out actually of the University of Florida. And the company was originally founded when it was really a tiny lab experiment in 2002. We worked in the UF labs for a number of years, actually got our first venture capital funding in 2006, became a public company in 2011, and really have been growing since that time period in 2011, moving to Tampa a couple of years ago with our labs and our corporate offices.
That's great. And as we want to focus on the startup elements of this company, even though it's a little bit of an older company, can you think back to sort of that transitional process from when you grew out of the lab and into its own company?
Yeah, no, really important phase and a challenging one for any company. And you need a lot of, especially in the biotech, medtech world, you need a lot of infrastructure to help support you. And that was one of the big advantages working within the university systems here in Florida, is that there's some great infrastructure to help support those startup technologies spinning out of the university. So we started in the UF, in some of the original research at the McKnight Brain Institute. That's where the originating technology came from. And then we transitioned into the incubator system with UF Innovate, the Sid Martin Biotech Incubator in Alachua, Florida, which is just outside of Gainesville. And that provided a ready lab for us to move into, such that from the time that we got our VC funding and then had the money to actually move into the lab and get started on the work, within a month, we were up actually doing technical work. Whereas if we had to build a lab from scratch, you're a couple of years out from being able to do that, and you're burning cash the whole time. So cash is king when you're in the startup world. You really got to use that cash efficiently to get to your milestones. And having that infrastructure really gave us a leg up to get going quickly. Healthcare takes a long time to get products to market. But from that time point of 2006, we had our first clinical implants at the end of 2007. Which is just a tremendous speed to be able to get that major milestone.
That's great. And from the equity standpoint, as the idea was birthed within the university, as you move into the incubator, is it the 10% type of thing where how do those conversations go with who owns what as you go out to seek outside capital?
Yeah. So the university, through the tech transfer system, generally, as we've experienced it, looks at it, but they want to make sure that there is value coming from the research that they're doing. And honestly, the percentages that you typically would see in that kind of tech transfer arrangement would be in the single digits as a percentage of a payment back on that license of the intellectual property. So they own the intellectual property. We have a license for all of the uses of it worldwide. And then that lasts we would continue making those payments through the life of the intellectual property. At least that's the typical type of agreement. So your startup team actually is the original owners of the company. But when you come in with venture capital groups, typically they're going to take majority ownership. And so that, I think, would be something any startup company would need to expect, is that when you work with the VCs, they're providing some very needed services, capital, that's obviously an important thing, but they also provide expertise in growing and scaling a business. And for that, they're going to want to have, as a syndicate, a controlling interest. So we had 3 VCs. They had a majority interest in the company. until such time that we obviously went public. And when you go public, obviously, then the public markets own you, and you're providing a benefit and growth for the public investors.
That's great. And getting into the weeds a little bit, just because I'm curious, though, if the university owns the IP, what happens then with derivative products? Is there some sort of litmus test for how connected to the original IP they are? If you come out with something that's a complementary product, if those payments are directly tied to the IP and they're not equity, then it sort of separates out the value prop for the university a little bit, right?
Yeah, so it really comes down to inventorship. If anything uses the underlying claims of that patent, so any follow-on products that we would have, obviously you're paying a royalty on the use of that intellectual property. If it is invented totally independently, and we have several products that are invented independently, then there's no payment, obviously, to the university. So our flagship product is Advanced Nerve Graft. That's what came out of the University of Florida. It's actually, in fairness, University of Florida and University of Texas, Austin is where we have the two sets of intellectual property. And we combined those two sets of intellectual property to create the product, Advanced Nerve Graft. And that's for that product. So we pay royalties on that product. We also sell a series of products called the Axoguard family, Protector, Connector, and Axoguard Nerve Cap, and they're developed independently and there's no payment or ownership rights for those through the university.
Got it. So let's look at that. First, look at that flagship product. Can you talk about it a little bit and what makes it special?
Oh, sure. So again, in the area of peripheral nerve, we are trying to work with surgeons when a nerve is cut. So when a nerve is cut, there's some special challenges in reconnecting it. So obviously you need to reconnect it so you allow signals to go back and forth. Just again, think about wires. If you cut a wire, electricity goes across. Same thing with nerves. But there's some special biological challenges in nerves that make them a little harder than wires to just put back together. And one of the challenges is when there's a segment taken out of the nerve. So think of in traumatic injuries or in things like surgeries where there's a tumor, where the tumor is adjacent to or even entrapping the nerve. When that is removed, you're going to have a segment of nerve that's now missing. And you can't pull nerve ends together. They don't heal. They don't heal under tension. So you've got to do something to bridge that gap. And that turns out to be biologically challenging to bridge that gap. In fact, the gold standard of what was done before we came into the market is they just say, what nerve do you want to give up? We're going to move a nerve from somewhere else in your body that's less important to you to use it to bridge this gap. So that meant as a patient, you always lost something to fix something. And with Advanced Nerve Graft, it is a way to bridge those gaps without sacrificing your own nerve, having a second surgery to harvest that nerve, and provide you that opportunity for functional recovery, while at the same time providing the biological cues that tell the body to repair and create a nerve in that spot.
So can you dig into a little bit to this? How are you doing that then with the solution?
Oh, yes, sure. So we start with tissue donation. So our nerve is made of human nerve. So in the tissue donation process, you can donate your nerves upon death, or you and your family do that. They are recovered, but obviously there would be an immune response if we use those nerves in a different patient. So we have a proprietary method that you can remove the cells and cellular debris from that nerve. So there's not an immune response. That turns out to be really challenging on nerves because they're tiny. And they're made up of hundreds or even thousands of little tiny tubes. So when you're extracting the cells, that you have to work them gently out each end instead of out of the middle, because you would turn the inside into no longer tubes. It would be a bunch of fractured pieces. And so it's a method of decellularizing. So you preserve those tubes. You also preserve certain biological cues that tell nerve fibers the direction to grow. So think of it as like lights on a runway tell the plane how to land. Well, these particular proteins tell the nerve fibers grow in this direction. And then lastly, it's been identified that there are certain proteins that shut down nerve regeneration. Just like in spinal cord regeneration, most people are familiar with that nerves, the spinal cord won't regenerate because there are certain proteins that just stop the regeneration process. That's also true in the peripheral nerves. And so we selectively go in and inactivate those proteins that shut down regeneration. And so in essence, we have a three-dimensional blueprint that the body recognizes as a scaffold to rebuild a nerve on. It gives directional guidance that says grow in this direction or follow this path. And we've removed those stop signs to regeneration. And that's the combination of pieces of intellectual property that create our flagship product.
Great. And if memory serves, isn't the growth direction DNA driven? So is this, are you tapping into working directly with the DNA to spur the proteins to do what you want, or is it past that point?
Oh, yeah, it's past that point. So it is actually it is a protein system that gives guidance cues to the cells, and so your extracellular matrix really tells the cells what to, especially undifferentiated cells, what to be and what to become. And so we're using that scaffolding system to help give cues to tell both the cells. So there's certain cells that migrate into this scaffold, but also the regenerating nerve fibers, which are really interesting because they come from a cell all the way back in your spine or near your spine, and they regenerate this long, thin tail, and they grow all the way through, for example, your arm, all the way to your fingertips to give you sensation in your fingertips. And we want those cells to grow, or those nerve fibers that come from those originating cells to grow in the right direction.
Got it. And again, just curiosity, digging in a little bit there. So when you look at the way you spoke of that, it made me think that with a donor body, there would be some more rare elements of certain nerves that just have one. When you originally said it, I had a thought that you could sort of take apart and match the nerves from different places in the body because you're essentially you're bringing them back to a generic state where they're just they have their utility, but some of their not, some of their specificity. So from a donor body, can you get how much usable nerve length can you get?
Yeah, no, really good question, because we are taking them back to the basic elements. So you don't have to match like a nerve from a finger to put in a nerve in a finger. You're really trying to match the size, but the scaffold is generic. If the same size is here in the finger and here in the face, you can use them in any place in the body, which makes donation pretty expansive. You can a single donor can affect many patients. Very often 20, 30 patients can be affected from a single donation. And they can make a real difference in people's lives. We work in the area of traumatic injuries. So power tools, kitchen knives, falling on glass, anything that is soft tissue related, you can end up cutting nerves. We work in the area of breast cancer. So women who have a mastectomy, traditionally when they would have a reconstruction, they weren't repairing the nerves. So for the woman, she might look normal, but she doesn't feel normal. She can't feel her children when she hugs them. That's important to going back to being normal again. And so we've started a program in resensation, but allowing sensation or restoration of sensation in the breast. We have a similar program in oral maxillofacial surgery. So these tumors of the face right here in the jaw, traditionally those patients would lose all sensation for that half of the mouth. And you have that same sense when you leave the dentist, right? Where you can't feel anything. You feel like you're numb and drooling and lisping, except now it's permanent. So that's a big impact on the way you have comfort in interacting with people around you. And we can allow those patients to have a restoration of sensation by reconnecting the nerves. And then our last area that we're focusing in today is in the surgical treatment of pain. So it has been identified that one of the substantial causes of chronic pain are actual physical anomalies in a peripheral nerve. So these nerve fibers, instead of going, like I said, I wanted to go a certain direction, instead of going there, they get tangled up and they kind of short out against each other and create this static back to the brain that the brain interprets as this burning, electrical, jolting pain. Well, that's a physical problem in the nerve, and you can stop those pain signals by cutting out the bad section of nerve. Well, now you have to fix it. You have to do something with it. So you can repair it with advanced nerve graft, or you can terminate it and end it with our Axogen nerve cap, but you can stop the pain, that bad section of nerve. And those are the sorts of things that we think you can do with the technologies that we have that really have a big impact on patients.
And once you start heading in that direction, then you could even get into more just everyday uses that aren't necessarily tied to trauma, right? That's
right. Right. Yeah. There's a lot of places to expand beyond trauma. We focused on the spaces I just mentioned before, just in trying to be methodical about how we segments, but there are many areas that we think that we can work in. We've done work, early experimental work, so put it as it's not ready for prime time yet. But there's work that's been done in when men have prostate cancer. There's significant morbidities in terms of erectile function and continence. And those are nerve injuries. And we've shown that you can repair those nerves using the robotic procedures. And we're an important area that we think down the road we'll be able to enter into. There's opportunities for people who have substantial dry eye. Sometimes they get so dry that they ulcerate the corneas. And there's an opportunity to restore that function and ultimately prevent blindness, which is what you want to stop there. So that's an interesting opportunity down the road. There's many areas in this area of surgical treatment of pain that I think we could expand into how peripheral nerves are one of the causes. They're not the only cause, but one of the causes. And they're one of the causes that today has gone untreated except for managing the symptoms. Well, we'd like to solve the cause of the pain. So those are the areas that we think we can continue to see innovation and expansion that allow a significant runway of growth for the company.
That's great. And given the the abundance of material and one donor and the technology that you've crafted, does that at this point diminish sort of the drive for people to find synthetic alternatives? Assuming that the real is available and usable, how does it sort of the threat of a synthetic option play?
Well, people tried to make a synthetic nerve for many, many years. You can make things that look like nerves. A lot of different technologies to do it, but the body wants. When you put a foreign body in it, it tries to wall off the foreign body. Now, it happens all the time. When you put in a hip implant, it tries to wall off the hip implant. That works fine in these bigger implants, but when we're talking about something as small as a nerve, what it ends up doing is plugging all of those little tiny holes that I talked about. So now there's a barrier to allow those nerve fibers to regenerate. So not only do you not have a pathway telling them the direction to go, but there is a brick wall in front of them, And so that has been a technological challenge to come up with biomaterials that are so biocompatible that the body responds and allows those small structures rather than walling them off. And so I think innovation will continue to advance. This is a challenge not just for nerves, but for all products. There would be better implants if they were more biocompatible. But it has not been an easy problem to solve. So while I applaud and continue to monitor all of the different types of innovation out there in biomaterials, we haven't seen anything that makes it imminent that there'll be a synthetic that will be appropriate for this application.
Delving a little bit back into the startup elements, can you talk about the growth of the company from being a single product company to a suite of products, and sort of, was that always the intention, or was it opportunity driven? How did that come about?
Yeah, small companies, I think, evolve. So it's a combination of both. We started with a single focus on advanced nerve graft. And as a small team, that was as much of the bandwidth as we had. But I think we pretty quickly realized that when a surgeon is addressing a problem in a nerve, that there are multiple challenges that they may have surgically. And one of the issues in nerve repair for that surgeon is that they don't know what the solution will be until they actually are in the surgery. Because there's no way to image those nerves with enough accuracy to know exactly what the problem is. And so it became clear that if we really want to be a solution provider, we need more than one solution. And so that was really the sort of aha as a company to say, oh, we were here to help the surgeon solve this problem, and we only have one choice. And sometimes they need different options. And that's where we brought in Axoguard Nerve Connector and Axoguard Nerve Protector. We partnered with a company called Cook Biotech, who had a particular biomaterial that we felt solved the need that we had. What we wanted was an Axoguard connector. Sometimes a sharp laceration, there's no gap, but they still need help bringing the two nerve ends together. So think of Axoguard Nerve Connector as biological duct tape. And so basically it seals the coaptation between the two nerve ends so the nerve fibers don't leak out and tissue doesn't infiltrate into the gap. And so it protects that gap. And then we have Axoguard Nerve Protector, which is the same material, but there are times where the nerve is intact. So think of a blunt trauma. The nerve's not functioning well. They go in and look and say, well, it's intact, but there could be a partial jagged tear on the nerve, or perhaps it's just the surrounding tissue is now crushing or impinging on the nerve. And they need to do something to help protect that nerve to allow it to heal. So that's what Axoguard Protector does, is it wraps around the nerve and basically creates a sleeve around the nerve that keeps the surrounding tissue up and off of the nerve and allows the nerve the space to heal. And so we really felt we needed to be that solution provider and found a really outstanding material that we could work with. And again, partnered with Cook to create those two products and add them into our portfolio. So we did that pretty quickly because we felt it was important strategically to do that. Then as a company, you always have this choice that says, okay, now we want to think about what's next. We have this great technology. We know how to decellularize tissue. We know understand how the proteins work. Maybe we should do that across lots of different types of materials. Or should we stay focused in peripheral nerve? Because you kind of have a decision of, are you going to grow along the technology or going to grow along the market? And we decided, we're really unique in the area of peripheral nerve. There's no other company like us focused in peripheral nerve repair. And we think we can have the biggest impact on patient care by focusing exclusively on peripheral nerve. So for example, we're not doing spinal cord. Could we do something in spinal cord? Maybe someday, but we really think there's enough impact that we can do in the peripheral nerve market that we've really zeroed our focus in on that and look to continue to expand and add products to help support surgeons solving problems with peripheral nerves.
Makes a lot of sense. Okay. And then the pot of gold at the end of the startup rainbow for a lot of people going public. Can you remember how you felt when that, from the discussions of that till it was official and you saw yourself on the ticker?
Well, we became public in a little bit of a different way. And we did it really when we were really small. So in the financial downturn in the 2008, 2009 timeframe, VCs no longer had money. And we were VC backed. Our VCs said we're going to prioritize our funding for our already commercial companies, and we didn't meet that profile. And we needed to figure out, how do we get through this soft spot in terms of the markets? And for a period of time, we went to high net worth individuals and had high net worth individuals invest directly in the company. Very appreciative that we were able to get that. But after a while, we still had to say, okay, this takes a lot of money to keep a medtech company, the experiments and development work going. We're going to need some more money than that circle of friends and family and acquaintances. And so we looked to start another round of investment and just saw that the VCs were still they hadn't finished raising money again following that downturn. So we turned to the public markets. Now, at the time, we were just barely commercial. I think we were between $2 and $3 million a year, way too small, to be honest, to be a public company, except that was the best last resort for us. So we ended up merging with another public company. We did a reverse merger. We merged with a company called Lectech. that was in a unique situation in that they had cash, but they had out-licensed all of their intellectual property and had some royalties coming in. That allowed us to put their cash to work. It gave us a platform to be able to raise money again in the future, which we used and then uplisted to NASDAQ. So it was for us survival to be able to raise money, but it was also really exciting to suddenly see our name, up in Times Square and on the NASDAQ board. We got to ring the bell at NASDAQ. That was a very exciting milestone for the organization. It does come with obligations, though. As a public company, you live in a glass house. You've got a lot of scrutiny on everything that you do. You give quarterly updates on things that are really long-range changes in the business. So it's hard to give sometimes those quarterly updates that really truly show what you think is the strategic progress of the business. But it allowed us to keep the company funded and provide the growth and impact that we've had today. So I'm happy to be on the public markets, but it's not for everybody. It's not for the faint of heart.
And it sounds like the company wasn't out there to be a vehicle for reverse IPOs. It was just you guys. So that's nice. Yeah. So
it wasn't a SPAC. So it wasn't, here today, people talking about SPACs and the way they started up. This was actually an operating company that we merged with. We ultimately shut down all of their operations. That they had nothing to do with our business, but it provided us the foundation we needed to be able to move forward.
Yeah, you got to do what you got to do. Wonderful. Well, I appreciate you taking us through your startup journey. I know you're a few years past that now and thriving. Want to finish up by talking about Tampa Bay. Why are you in the area?
Well, again, we started with roots in Gainesville, loved Gainesville, and saw a tremendous amount of support from the university in town. But as we grew and still grow by recruiting talent. We have about 400 people today, so we have grown substantially. And many of those we recruit from biotech, medtech markets. So I think in Boston, Minneapolis, the Raleigh area. Those are areas that a lot of medtech people reside, and we needed to be able to attract that talent, especially mid-career talent. And that was a challenge to Gainesville. Gainesville is a great college town, but for mid-career, dual career couples, it was harder to get people to move there. And so we did a nationwide search and decided where do we want to move our headquarters and labs to, and ended up finding that Tampa had everything that we were looking for. We wanted the things that make people happy and families happy when they move. So good schools, good housing, diversity of housing, transportation, a good airport, and a vibrant city with lots of things to do. And we found all of that in Tampa. We found and had a custom purpose-built facility. We leased the facility, but built out the labs in the new Tampa Heights area in the development at Armature or next to Armature Works. So it's a great area right there on the river. In fact, especially in the labs, we just have to show people the building and the labs, and they go, "Okay, I'm in," because it's such an attractive location, and the labs are spectacular. It really creates a recruiting tool for us to attract talent now.
Karen Zaderej, thank you so much for again sharing your startup journey. I've enjoyed the conversation, and we'll look forward to keeping an eye on your success moving forward.
Thank you very much.